So the way that this warm-up is currently written, it's not friendly for the methods that we've learned when taking the derivative. So what do we have to do? We have to move the 2x to the third over to the other side with subtraction. So I like to just rewrite this in standard form. And now we're ready to take the derivative of both sides. And this is the notation I'm going to use today. If I want to take the derivative of this entire piece, I call it d dx. Well, watch what happens to the left side. If I take d times, think of this as 1 over y, or y over 1, d times y gives me dy, and then dx times 1 is dx. So this is the derivative of the function with respect to x. And then what do? If I take the derivative of each piece here, the chain or the power rule, 3 times -2. We take 1 away in the exponent. Technically, there's a 1 here. This comes down and multiplies by the -4. And I get x to the 0, which is 1, so we don't write that. And the derivative of a constant is 0. So here's the derivative of the, oops, I don't want to put that in. Here's the derivative of the, or the first derivative of the function. Well, now, what if I want to take the derivative of this answer? I'm just going to do dx again. Now watch what happens, and it kind of explains why the 2 is in the spot where it is. D times d is d squared, and then the y is just multiplied right there. Dx times dx is dx squared. Don't ask me why they don't put parentheses around there. I'm not really positive, but it just refers to the entire thing being squared. But this is just stands for the notation of the second derivative, the power rule on the inside, the derivative of a constant is 0, and here is the second derivative. Now, what I want to just point out is this is called explicit differentiation. Not the notation here, but just solving for y and then taking the derivative. Everything we've done up until this point, up until today, is going to be explicit differentiation. Today, we're going to do implicit differentiation, which means what happens when x's and y's are mixed together. And sometimes we can't separate them nicely like this example, so how do we find their derivatives? And that's what we're going to explore today. All right, this one was just an extension of what we did in Unit 2. We just haven't done this in a while, and I want you to be aware that these problems will continue to come up. The first thing is this cube root. Now look at my notation. I'm not doing any calculus. I'm just rewriting the meaning of this. And instead of doing the cube root, that's the same as the 1/3 power. And then this is referring to taking the derivative of both sides is my chain rule. I have the outside function, which is the 1/3 power. And then I have the inside function, which is the x to the 7th plus 2. So if I'm going to take the derivative, I could do the same d dx notation as I did over on the other side, but I don't need to. So let's just use our regular notation here. So if I take the derivative of both sides, we're going to deal with the outside function first. That's the 1/3. So the 1/3 is going to come down. And then we take 1 away. And I always like to subtract the creative form of 1. So think of that as 3/3. That gives me -2/3 up top. And then the chain rule is the derivative of the outside. Keep the inside exactly the way it is. And then multiply by the derivative of whatever this inner piece is. So this is just a power rule. 7x to the 6th. The 2 is 0 when we take its derivative. Now technically you're done there. That's the correct answer. But if this was a multiple choice question, we'd have to learn how to rewrite this. So think of the 1/3 as my fraction. And then this whole part here is raised to the -2/3 power. So let's use blue. So then the x to the 7th plus 2 is going to come down and become a 2/3. And then the 7 times x to the 6th, you can think of that as over 1, which basically means this is going to be in the numerator. I really don't need this 1 up top because 1 times 7 is still 7, x to the 6th. And this would be an acceptable answer. It might be written like that, multiple choice wise. Or the only other thing they would do is deal with this 2/3. And I think that's a really important thing for us to focus on is what does the 2/3 look like? Well, there's a few ways to write this, but here's the way I think of it. See this divide by 3 right here? The denominator of the fraction, that divide by 3 is the same as the cube root. So you can think of this as being a cube root. And then the squared could go on the outside or the inside. I might just put it on the inside like that. So this is probably the way it would be written if it was a multiple choice question. If you're writing this out by hand, I would tell you to stop right here. Okay, so a couple things before we jump into our learning today. The first one is I want to quick talk about signing up for the AP Calculus exam. Some of you have already done that. Some of you haven't. And I want to just give you a quick reminder. So if you go to our Schoology course and we're in week 9, under that folder, you see our agenda. So here's what we're doing today. Here's the homework. Wednesday, there's no school, like no extra learning. So it's a good time to get caught up on missing work. And I just put sign up for AP Classroom if you haven't already. That's what we're talking about here. And then Friday, we're going to do more on what we're learning today. But then right at the end of the folders, I put sign up for AP Classroom and the AP exam. If you click on that link, it has our class code. Ooh, it doesn't. Sorry, I will switch this. We need to have our 2nd hour class code. This is my 5th hour class code. But if you click on the link, it brings you to I think it's 8 steps to join. You just follow these 8 steps, and then that will get you signed up for the test. Now, why do you want to do this now? Well, here's a couple reasons. If you're not sure if you're going to take the test, sign up anyways because it's free to cancel this year. There is no fee to cancel. However, if you're not sure and you wait and then you decide you want to, there's a $40 late registration fee. You have to sign up by November 13th at the very latest. Otherwise, it might be on that day or after that day is when you have to pay $40 to sign up. So please make sure you just sign up because it's easy to cancel, right? All you do is we won't send you a test if you're no longer in the class. So if you were planning on dropping the class, if you know for sure you're going to drop the class going into 2nd trimester, then you don't have to sign up. But if you're not sure and you decide at some point 2nd or 3rd trimester that you're going to drop calculus, then it's easy to just cancel the exam. There's no fee. But you can't do it the other way around without paying the $40. So that's your goal here. Sign up, write yourself a little note, send yourself a reminder on your phone to get signed up soon. I would do it this week. Okay, what's left in trimester 1? Well, let's take a look at where we're at. I want to lay out the weeks we have. So we're on Tuesday right here. We're doing implicit differentiation. We don't have school tomorrow. And then when we come back, we're going to have a little quiz, and then we're going to do implicit differentiation again. The quiz will be taken after we learn more of the notes. And then we've got a couple more sections. We've got 3.3 and 3.4, a review day. Then we're going to have a test on Unit 3 in class on the 9th and 10th. So that's either Monday or Tuesday, depending on when you see me. Those of you who will be in school for that day for hybrid, we'll talk about how that's going to work. And then we might even have a little video at the end of this day that helps introduce the next couple of units. But then we get a little bit of chapter 4 or unit 4, which is a pretty small unit. And then we have finals. Now I want to just quick mention finals. Finals are not going to be like a heavy weighted grade. The finals are going to be the same amount as every test. So this test in Unit 3 is 50 points. This test right here will be 50 points. Now, it will include some questions from all of the units we've learned. So you do have to think of this as a cumulative final. But the nice thing about calculus is we keep using and using and using the same things over and over and over again. So it's really not going to feel cumulative. It's going to feel like we've already done this stuff and we just keep getting better at it. One really nice example is write the equation of a tangent line given a function and a point. Okay, so far we've had that on almost every test, and you'll have it on this test. So just so you're aware, that's what's coming up. Okay, so we're going to start here with implicit differentiation. And I usually don't like to give step-by-step instructions because it doesn't always work that way in calculus, but for implicit, it actually kind of does. This is 3.2, day 1 in our textbook. Implicit differentiation is when we're going to take the derivative with both sides with respect to x, which means it doesn't matter what the left side and the right side look like. We're just going to take the derivative with with respect to both sides. And our way for kind of doing that symbol of taking the derivative is going to be that d dx. So you'll get used to that notation today. The tricky about this whole process is what happens when I take the derivative of y and what happens when I take the derivative of x. They're two different functions. So how's that represented? One of them is the dy dx appears. So I'll just kind of show you the 4 steps, have you write them down. We're going to collect all the terms, dy dx, on one side of the equation. Then, if possible, we're going to factor out a dy dx and then isolate it. Get dy dx by itself, and that's the derivative. So the act of doing this will allow us to achieve the derivative of the function. Okay, so you don't really have to write this part, but what does that mean? When I find the derivative, well, that's the derivative of the function. Well, this will help us find the slope. Dy dx, think of that as the same as your slope. That's your derivative equation. And then it's likely that we'll have you use this derivative problem to solve other problems, like find the equation of a tangent line. You need a point, you need a slope. So we're going to show you the exact same problem you guys just did. And we're going to do it, but using implicit differentiation. And I'm not sure if you want to write this one down. It's up to you if you want to write it down. I'm going to go somewhat quick. We're going to do a lot of this, so maybe you don't really need it, but sometimes it's nice just to see the process first. So what do? Step 1 is differentiate both sides. Now, once you get really good at this, you can kind of skip this step, but officially, we should take the derivative of both sides with respect to x. All right, now, when I do that, since there's no product rule or quotient rule here, it's just a power rule. The 3 comes down. 3 times 2 is 6. And then I get x squared. However, we're taking the derivative with respect to x. So the d is going to multiply by x. So I get dx on top over dx on bottom. And eventually you're going to learn that you really don't need to write this part right here because dx over dx is the same thing and that reduces out. But I've found that my students that write this are more successful when doing these problems. So it's one tiny little extra step, but in the long run, it really pays off. All right, now I have to take the derivative of y. Well, technically, there's a 1 up here. The 1 comes down. And then this becomes 1 minus 1, or y to the 0 power, which goes away. However, we're taking the derivative of y with respect to x. So the dy dx does not reduce out, because these are not the same terms on top and on bottom. And this is extremely crucial that you write this step. It's the part that students miss the most, is when you take the derivative of anything that has a y, you always have a dy dx that follows. All right, now what if I take the derivative of the other side? Well, the derivative of 15 is 0. You don't have to write that. And then the derivative of negative 4x is negative 4 dx dx. All right, so just anytime you take the derivative of something with an x, a dx dx follows. You can kind of think of that as like the chain rule. Anytime you take the derivative of y, you get dy dx that follows. Well, now that I have everything written out, what I do then is say dx over dx is going to just turn into 1. That's going to reduce out. So any spot I have a dx dx, that turns into 1, which shows you that when you really get good at this, you don't have to write those. But what's left over then? X squared plus, we usually don't write the 1. I get dy dx minus 4. And then I don't have to gather all the terms because there's only one dy dx. I just have to solve for it. So that means the 6x squared is going to move over. And the derivative dy dx is equal to, and then I usually like to write the squared term first. And there's the first derivative. Okay. Then it says find the second derivative. Well, this again is getting used to notation, so I'm going to leave myself just a little bit of room so we can practice proper notation, and I hope that's your goal. You're not looking for short ways to do this, you're looking for accurate ways step by step that I'm modeling. So I hope you're paying attention to step by step process. All right, so what do? We need to take the derivative of the derivative, which means we're going to take d dx to both sides. And then this is the notation we talked about. D times d gives me d squared. And then the y just stays. Dx times dx is the dx squared, and that's where this notation comes from. And then I have to take the derivative of each piece. Well, inside, this is just the power rule. I get negative 6 times 2, which is negative 12. X to the first power. But then we took the derivative of x with respect to x. And then the derivative of negative 4 is 0. You don't have to write the plus 0. You say minus 0 because that part doesn't change. So then the last part is realizing that the dx dx is going to cancel out. And you're left with 1. Okay, so I don't want you to write these problems. I want to go through this as quick as possible, and it's really nice just to see the notation and take it all in. So don't write these. If you ever need them, they are going to be on this video that I'm making or on our filled out notes. So let's go through this quick. We have to find dy dx. Well, notice right away, the y is really complicated. There's a lot of stuff going on here. Now, we could solve this for y and try to take the derivative of that, but we run into a problem when I move cosine over here, it becomes cosine inverse. And right now, we don't know how to find that. And then we've got the other problem that has x's and y's joined together. So when you see things that are complicated like this, we're going to do implicit differentiation. And what do? We're going to take the derivative with respect to x of both sides. Right? Why is it with respect to x? Because that's our independent variable. So what do we got? 7 comes down, multiplies by 5, and I get 35x to the 6th times dx dx. Right? I took the derivative of x, so I have to write dx dx. Kind of like the chain rule if you want to think of it. Now I have to take the derivative of this left piece, which there is a chain rule here. I've got my outside function, which is cosine, so its derivative is negative sine. We're going to leave the inside, and then we're going to multiply by the derivative of the inside. Well, the derivative of 3y squared, the 2 is going to come down. That's 6y to the first power. But then I took the derivative of y, so I have to have dy dx. And that's the part, now it's the only spot where dy dx shows up. So the rest of my work is trying to isolate this and move everything over to the other side. The only thing I'm going to do is say dx dx reduces down to 1. So there are some steps you can skip when simplifying. And here's what I got. I've got 35x to the 6th is over here. Now this whole chunk is being all multiplied together by the dy dx. So let's just divide both sides by this whole piece and move it over here. I'm going to do this just a little bit of simplifying. The 6y is going to multiply by the negative. So I'm just going to put that out in front. And then the sine of 3y squared is going to just stay put. And then the only thing that's left over is dy dx. And remember what we just did. We found the derivative. This is the equation for slope. So if you have a point, if you had the point x equals 0 and y is equal to 2, you could plug that in here and here. You could plug in x equals 0 and y equals 2, and you could find the slope at this point of the tangent line. Notice how x's and y's are combined together. That's what implicit differentiation allows us to do. All right, this one's a little bit tricky. There's more than one way to do this problem, and you could deal with algebraic properties. There's an easy way and a challenging way, I guess, to do this. I'm going to just pick the way that's currently given. I'm going to make a little bit more room in this problem. So what am I going to do? Take the derivative with respect to x. So I'll take dx of this side, and then dx of this side. Well, there's a chain rule for this side here, and I think this one I'll highlight one color. The outside function is e to the x. The inside function is x plus y. So if I'm going to take the derivative of the outside, that's just e to the x, but in this case we're going to keep the inside piece exactly the way it is. And then I'm going to multiply by the derivative of the inside piece, and this is where you have to be careful. The derivative of x is 1 dx dx plus the derivative of y is 1 dy dx. And notice how I put that in grouping symbols because that's being all multiplied by the chain rule, beginning of the chain rule. And then over on the other side, the derivative of y is just dy dx. I'm going to put that in blue so you'll see what we're doing here. Well, okay, we took the derivative of both sides. Now I have to use algebra, and I have to get both dy dx's over to the other side, but I've got a small problem here. This is being multiplied. So I actually have to distribute first before I can try to isolate the dy dx. When I do that, oh, by the way, dx, ooh, dx just turns into 1. So this is really, this whole thing is 1 times 1 or 1. Well, let's distribute. So if I take e to the x plus y times 1, that stays. And if I take e to the x plus y times dy dx, which is going to look like that. So now I can move the dy dx, I can move this whole piece over to the other side. And that's just with subtraction. All right. So now my goal is to get the dy dx by itself. Well, the only way to do that is to factor. What do these two pieces have in common? They both have a dy dx. So I'm going to pull out a factor of dy dx from each side, from each piece. And what's left over then is if I take a dy dx away from dy dx, there's a 1. And what's left over here is e to the x plus y. And then we didn't do anything with the left side yet. And then the very last step is to get dy dx by itself. Well, dy dx is multiplied by this whole piece, so I'm just going to divide it over. And what's left over is dy dx. Now, don't get scared, okay? This is kind of challenging, but we'll get there. And eventually you're going to look at this problem as pretty routine. Okay, so let's try this one. I definitely want you to write this. And the reason why is what happens when I combine implicit differentiation with some of the terms that we already know. Okay. Pay special attention to the instructions. When do we have horizontal tangents? And when do we have vertical tangents? Well, what we have to do is we have to figure out what do we know about the derivatives of horizontal lines and vertical lines. Another word for derivative is slopes. So here's what I'd like you to think of. When does the function have horizontal tangents? What do we know about the derivative of anything that has a horizontal tangent? What's the slope of any horizontal line? Horizontal line goes left to right. The rise over the run is 0. So we're looking for when, what point, what x's and y's combination gives me a 0 slope. And then what do we know about horizontal, or vertical tangents? Vertical tangents are up and down. What do I know about the slope or the derivative of a vertical line? That's when it's undefined or it doesn't exist, right? So when is it undefined? That's what we'll have to look at. Well, to answer these questions, I need to find the derivative. Let's see, this won't. Okay. I don't have enough room to put a space in here, which is fine. But since x's and y's are on the same side, yes, I will acknowledge you could solve for y here. And you'd have to do a chain rule. which is still completely doable, but implicit in my mind is a lot faster. So I'm going to just say I have to take the derivative of the entire thing with respect to x. Well, there's no product or chain rules or anything. This is just a power rule. The 2 is going to come down. And then I'm taking the derivative of x with respect to x. Think of that as dx dx. If I do the same thing on the y, the 2 is going to come down. I get 2y, but then I'm taking the derivative of y with respect to x. And then the derivative of the 25. A lot of students forget about this. You have to take the derivative of all sides. Well, the derivative of 25 is a constant. It's just 0. All right? Well, now the dx dx will always reduce out, but dy dx is what we want to solve for. You might be able to do this all in one step, right? Because you're going to have to subtract the 2x over to the other side. And then you're going to isolate the dy dx, so you have to divide by 2y. If you can do that in your head all in one step, then you don't have to show multiple algebra steps of just solving. And you might even realize that, hey, the factors of 2 are going to reduce out. So algebraically, here's my slope. Right? That's your derivative. This is the equation. That's how we can find slope. So now that we know what the equation is for the slope, let's explore horizontal tangents. That is when the derivative is equal to 0. Right? And that's our justification right here. dy dx has to equal 0. Now it's just algebra. You need to solve, well, the way I think of this, if I have a number equals a fraction, I like to think of it as cross-multiplying. And you're going to notice if you cross-multiply 0 times y is still 0. So what are we really doing? We're just setting the numerator. And that's true for any derivative for horizontal tangents. You just set the numerator equal to 0. And then you solve. Well, 0 equals negative x. If I divide by negative 1, I get x equals 0. But when is referring to the point. I need to figure out what location, which is an x and a y. So the only tricky part here is once you find what x is, you got to find y. And that's always going back to the original equation. So x squared plus y squared equals 25. But we know that x is equal to 0. And now it's just more algebra. Here you get 0 squared. If y squared equals 25, then I'm going to take the square root, and I'm going to get 2 answers. I'm going to get a plus and a minus. So now I have 0, 5, and 0, negative 5. So this answers the question of when do I have horizontal tangents. Now you should just double check. Does that make sense? If I plug 0 and 5 in here, does 0 squared plus 5 squared equals 25? Yep, this one works. Does 0 negative 5 work? Well, 0 squared plus negative 5 squared is still 25. So I did check both of those mentally, and you kind of always want to be aware of that. All right. Well, what about vertical tangents? What do we know about the derivative when we have a vertical line? When is the derivative undefined? So if this is my derivative equation, what's the only value that makes this fraction undefined? In general, anytime you're looking for vertical tangents, let's do this. We always set the denominator equal to 0. Because that's the only time that this fraction will result in a undefined answer. Which means it doesn't matter what x is in this case, y just cannot be 0. So vertical tangents will occur when y is equal to 0. But if we find y, then we have to find x. Just like we did in the example here, we had x. So now we have to find y. Well, now we got y. So we have to find x. And you're going to probably know this answer already if I plug in 0 for y. You could solve this in your head. X squared equals 25. If I take the square root, I'm going to get 2 answers. So now my horizontal tangents occur at 5, 0 and negative 5, 0. Okay, so officially we're done with this problem. If you wanted to, though, you could check. Well, how would we check? What if I graph the original equation? And you might remember this from Algebra 2 or pre-calc. X squared plus y squared is equal to the radius squared. Well, in this case, the radius is 25. This is just the equation for a circle. And notice those important, and it's centered at the origin. We don't do a lot with equations of circles, but they pop up every once in a while. Now here's where you have to use your imagination. Pretend I am drawing a really nice, perfect circle. Not even close. But what did we just find? Well, at the spot over 0 up 5 or over 0 down 5, what do you notice? The slope is 0, which is dy dx. dy dx is equal to 0 here and right here. The tangent lines. Those are my 0 slopes. Well, then where do the vertical tangent lines occur? At the spot positive 5, 0 and negative 5, 0. This should be an X. Didn't look like one. And then over here, undefined slope, vertical tangent. So we're not always going to have the luxury to have a nice graph, but this is a friendly equation. If you remembered it, it justifies it. Now, let's say that this was a test question. If you didn't show the calculus work to this problem and you just answered the question, cool. I might give you 1 out of the 7 points. You get this class is a calculus class, so we need to show calculus methods when solving problems like this. All right. So we for sure got one more example, and we might even try a second one. But what happens if it gets a little harder? Because this one wasn't too terrible. There wasn't a chain rule or product rule or anything, quotient rule mixed in there. So we're just going to look at a little more challenging one and see how we can do with that. Notice the directions. Write the equation of the tangent line. We've answered this question probably 20 to 25 times so far this year in the homework and quizzes and tests. And you're going to answer it probably another 50 to 100 times more. All right, write the equation of the tangent line. Well, my brain right away goes to the point slope equation. And we have to find the equation at the point. Well, that's nice. They give us x1, y1. The only thing that they don't give us is the slope. And you need to remember, well, what is slope? Slope is just the dy dx. It's the derivative. So that's the hard part about this problem is, all right, now I have to find the derivative. Well, look at how messy this is. I've got x's and y's together. I've got a sine or a pi, that's just a constant, and then I have the sine of y. So there isn't any true quick way of isolating y, so I get the equation y equals, which means the only way to do this problem is the implicit differentiation. So that's our work right here. So we've got find slope, find the derivative. Well, we're going to take the derivative of both sides, and I write it like this, and this isn't perfect notation. The dx should be in front here, but you guys get the idea. We're going to take the derivative of both sides. We have a small problem right here. I have a u times a v. I have to do the product rule. Now you could, off to the side, write u prime, v prime, and follow the product rule. But I'm really hoping that you can do this part kind of in your head. And that's where the saying of the product rule comes into play. All right, what is it? Well, it's the derivative of the first piece. So the derivative of 2x is just 2 dx. That's the derivative of this part. And then we're going to multiply that by the original second piece, which is just y, plus the second or the first original piece, 2x, times the derivative of the second piece. Well, what's the derivative of y? That's just 1. You don't have to write the 1, dy dx. So this whole piece is the product rule, and it came from right here. Nothing super crazy. And then we're going to take the derivative of pi. Now pi is a constant, So that's just a multiplier. But I have a chain rule here. I've got sine, and then inside of the sine is y. So the derivative of sine is cosine. Keep the inside, we're doing a chain rule here. And then we have to multiply by the derivative of the inner part, and the derivative of y is 1 dy dx. So that's the derivative of the left side. We had a product rule to get the first part, and officially a chain rule to get the second part. And then over here on the far right, the derivative of 2 pi, that's a constant, so it's equal to 0. All right, now the only spot that's going to reduce out, dx over dx is equal to 1. Well, now notice, look at the 3 pieces to this equation. I've got 2 times 1 times y, so this 2y is the only piece that doesn't have a dy dx, so it's going to move over. I'm going to subtract 2y over to this side. This part comes over. And then look at what's left over. Both of these pieces have the blue dy dx. So I'm going to factor that out. And what's left over is just the 2x plus pi times cosine of y. Remember, our whole goal is to get the dy dx by itself. All right, well, this is dy dx times this whole piece. So if I need to move this whole piece over to the other side, it's going to be divided. And sometimes we can check to see if things can be reduced. If there was another 2 here, I could factor out a 2. These two 2's do not reduce out. All right. It's always important to understand, what did we just do? We found the slope equation. Well, I need the slope at this specific point. So to answer the final question of writing the tangent line, to find the slope, now I just have to plug in 1 for x and pi over 2 for y wherever I see it. And what I've noticed on the test is students are missing the idea of, when we say slope, it has to be the slope of the point. So that's where we have to plug this in. There's a notation that I want you to be aware of here. So we know what our derivative is equal to. And what I'm going to do is I want to evaluate the slope at this point. So see how I drew a line and then they put the point at the bottom? That's your symbol for just saying x is 1 and y is pi over 2. Plug those into the derivative equation. I'll give you a second to get caught up here as soon as I plug these in. So I take my derivative equation, and I'm going to plug pi for pi over 2. That goes wherever there is a y. And then wherever there's an x, we put the 1. So now the rest is just simplifying. The top part is friendly because this is 2 over 1. This negative 2 and 2 divided by 2, they're going to reduce out. And I'm left with negative pi up top. And then on the bottom here, we get 2 plus, and now we have to figure out, this is where if you memorize the unit circle, you know this answer without doing any work. But if I'm at pi over 2, that's at the spot over 0 up 1. What is cosine of pi over 2? Cosine is always the x value. So this whole thing is going to be 0. So pi times 0 is 0. 2 times 1 is 2. My final answer for the slope is right there. Negative pi over 2. And then to finally write the final answer, write the equation of the tangent line at the point when x1 is 1, when y is pi over 2, and then we found the slope at that point. We're done. You could distribute and solve. That's not going to be super friendly, so I'm just going to leave it just like that. Okay, I do want you to notice one thing. See how I have my slope here? And I didn't write the equation right here. Yes, this is the slope, but it's not the slope at the point. So don't take this equation and write it in the spot for slope. You need to take the point that you're given and find that slope. That's a lot of students made that mistake on the last test, is they wrote an equation for slope. We want a number, right? And the point is what gives us that number. All right, so my last hour, because they had the hybrid day and they got cut short with lunch and they're behind just a tad, ended here. And I think it's a good spot to end. On Friday, we're going to do these two examples, which is where are horizontal and vertical tangents, and it's just an equation that we do the same thing we did in the last example. So you know how to do this. And we also know how to do this one. Where are their vertical tangents? The only thing I want to point out in this problem, see how it says x squared times y? You're going to have to do a product rule here. And then you're subtracting x times y squared. You're going to have to do another product rule when you find the derivative. So if you see that in the homework tonight, you're going to have to do product rules. You might even have to do a quotient rule using the implicit differentiation. All right, so here's what we got. Homework tonight is a handful of problems. These answers are completely worked out in our homework section on the main Schoology page. It's under Unit 3, Section 3.2, Day 1. I encourage you that as you're going through, if you do number 5 on your own, and then go check it in the on the homework, and just make sure you're doing it right, showing all the proper steps. Okay, and that's usually the best way to approach a difficult concept like this when you're first learning it. So we've got 13 minutes. If you have questions from last night's homework, the 3.1 day 2, or you've got questions in general that you want to stick around for, you can stick around and I'll be here for about another 13 minutes. But if you feel like you got this and you know what you're doing, remember there is no class on Wednesday. So your expectations for Wednesday, hopefully, is if you have any missing homework, get caught up. take advantage of Wednesday being a no new material day for any of your classes and get caught up in your other classes. And then please sign up for AP Classroom if you haven't done that yet. All right, that's all I have for you. Adios. If you got questions, stick around and I can help answer those. No, great question. So when we say sign up for the exam, by signing up for, let me just throw this over here. When we showed you that little on under week 9, I put a link how to sign up. I have to go change the code right now. That's what I was going to do. But by signing up for the AP Classroom, that automatically enrolls you into signing up for the exam. So you can do everything at your computer. You don't have to go into school. And all you have to do is join. And by joining, you're automatically enrolled in the exam. So I'm going to do that right now. I'm going to get this code. I just have to find it.